Good to be here at Bradbury Heights Elementary School. Let me ask, do any of you ever need to navigate? Is math and science, are they involved in being able to navigate? And how does navigation tie in with matters pertaining to safety? Now, I know you're wondering, why am I standing here next to this traffic signal? Can anyone tell me who invented the traffic signal?
Garrett A. Morgan.
Garrett A. Morgan. Very good. Now let me ask, can you imagine a city without traffic signals to help us navigate? Well, I can tell you, 75 years ago, that was the case. And that's when Garrett A. Morgan, an African American, saw a collision involving an automobile and a horse-drawn carriage. And so he invented this navigation aid that helps us, as we come to an intersection, move through it safely. Now, all of navigation, though, doesn't just control the way we move on the ground. As a matter of fact, what Garrett Morgan did with this traffic light, we are now doing with satellite navigation aids in the skies, and NASA is helping us to do that. Now, before today's program ends, you're going to be introduced to the wonders of satellite navigation through the persons of Van Hughes and Shelley Canwright, the hosts of NASA Connects. Watch and be inspired.
Hi, I'm Van Hughes, and welcome to NASA Connect, the show that connects you with the world of math, science, and NASA. I'm supposed to be meeting my friend Dr. Shelley Canwright somewhere around here at NASA Langley, so we can start off our show about navigation. Well, in today's show, you'll meet students from Northampton Middle School on the Eastern Shore of Virginia who were given a special navigational challenge. You'll also meet researchers here at NASA Langley in Hampton, Virginia, who will show us new forms of navigation. Oh, and when you see this symbol, that's your clue to check out more information, fun, and activities on the NASA Connect website. So, to start things off, Shelley has a special event lined up for us, so let's go check it out. Hey, Shelley.
Oh, hey, Van.
Finally, I found you. What's going on?
Oh, this is so neat. We're going to be in a road rally.
A road race? That's awesome.
No. This is not a race against time or speed. This is a race that's involved with how well we can navigate accurately. Something you probably could stand some help on, Van. Oh, hey, and this is Brad Ball. He's from the Geographic Information Team, and he's in charge of the road rally.
Hey guys, Shelley, Van, this is a special road rally. No maps allowed. We're only going to use GPS receivers.
What's a GPS receiver?
GPS stands for Global Positioning System. This little device, a GPS receiver, is the future of navigation.
So just how does this GPS receiver work, and how are we supposed to use it in this road rally?
The Global Positioning System is a constellation of 24 satellites that orbit the Earth. GPS makes it possible for people using ground receivers to determine their geographic location. By measuring the travel time of a signal transmitted from each satellite, a receiver can calculate its distance from the satellite. When receiving the signals from at least 4 satellites, a receiver can determine the latitude, longitude, altitude, and time. If the receiver is equipped with a computer that has a map, the position is shown on the map. If you are moving, a receiver may also tell you your speed, direction of travel, and estimated time of arrival at the destination.
Oh, okay. I think I understand now how we're supposed to use this receiver in this rally. This receiver will help us navigate to each of our destination points, but we only have a certain amount of time to get there.
Which means speed is important. So, I'm driving.
Wrong, Van, on both points. In a rally, you maintain the posted speed limit. Using the posted speed limit, plus the distance to each checkpoint, we have calculated the time it should take you.
Time equals distance divided by speed.
Right. Now program this receiver with your checkpoint coordinates. Your challenge is to find each point. The time and accuracy of finding each point contributes to your score. Shelley, you're the driver. Van, you're the navigator.
Okay.
One final rule. Here's your logbook. This must be signed and time-stamped at each checkpoint. Also, at each checkpoint, you're to collect the information on the navigation and how GPS applies to the featured site and get a clue to the next leg of your trip. Wait for the green light. I'll send each crew 1 minute apart.
All right, Brad, I think we're ready, okay? All right, all of us, how about hopping in? We've got room in the back. You can come along, help us collect the information, and maybe look over Van's shoulder. He'll probably need the help. Let's go.
Still thinking you should have let me drive.
Hey, hey, hey. Navigate, you navigate, I drive.
Wow, this is awesome. There's a computerized map on this receiver. It says that we have to go northwesterly, so... Oh, take a right here.
Right here, got it. Van, are you sure you have those coordinates right? We're coming into Busch Gardens, Williamsburg. Okay, listen, Van, I think you got us to the right place. Read some more on the GPS instructions. I'm gonna take this and see what I can find out, okay? And I'll be back in just a few moments. Busch Gardens. The bearings say here, Feathered Follies. Okay. Hello, excuse me. Am I in the right place? Is this the first leg of the road rally?
Yeah, come on down.
Oh, great, fantastic. Oh, Van, my man, you got us here. You navigated us correctly. All right. Oh, I am so relieved. Hi, I'm Shelley Canwright.
I'm Denise.
Oh, I'm so glad to know I'm at the right place. Here's my rally log.
Okay.
If you could sign that, please. And I'm curious, where am I? What is Feathered Follies?
This is the Feathered Follies Bird Show at Busch Gardens. And what we do here is we have hawks, falcons, owls fly through the theater. We have different types of parrots that do different behaviors to entertain the audience, the guests while they're here.
So what in the world does Feathered Follies have to do with navigation or GPS? I'm confused.
Well, all our birds that are here out in the wild, they do some type of natural migration. Songbirds migrate at night. They follow the stars. The birds of prey, they migrate during the day so they can move with the way the sun changes. They're following mainly their food and looking for warm weather.
What is the farthest that a bird has ever migrated? Do you have any
The
idea?
Arctic tern is the bird species that migrates the most, and they can go from northern Greenland down to Antarctica.
Wow, no kidding. This is fascinating, but I know I need to be on my way. So you've got some instructions there for me?
Yes, your next leg is going to take you to learn about early navigation.
Early navigation. All right, gang, you heard that? Back to the car. Let's get Van and let's go. Denise, thanks very much. We're on our way.
Good luck.
All right, thanks. Van, you were right. You do know how to use one of these things.
What did you see?
Oh, this is so neat. Birds. I learned how birds can navigate by instinct.
Well, gee, that makes me wonder if the GPS could be used to study animals in nature. Did you find our next clue?
I did. All I know, though, is it has something to do with early navigation.
Well, let's go.
All right, let's get out of here. Okay, is this our next stop?
Mariners Museum. There has to be something on navigation here.
Excuse me, are you with the NASA Road Rally?
Yes, I am. Do you have your logbook with you?
I sure do. Now, according to our instructions, we're supposed to learn something from you about early navigation.
Well, here at the Mariners Museum in Newport News, Virginia, we tell the story of man's conquest of the seas. When people set out to explore the oceans, they had to create a system of measurement to determine their location. To determine the distance along north to south, the navigator had to determine the altitude of the sun. For instance, if the sun on the equator at noon is 90 degrees to the horizon, and if the sun at the North Pole is 0 degrees, then the degrees in between note a ship's position. This is called latitude. To locate his east to west position, the navigator had to measure the difference between local times. For example, when the sun was at noon in different places. This is called longitude, and spring-driven clocks were a great boon to determining that position. Although the cross staff, the magnetic compass, and the spring-driven clock were high-tech for their day, ancient mariners continued to navigate a lot by what we call dead reckoning. That is, by estimating the position traveled from a previously determined position. I see you have one of those GPS contraptions. That's the way to navigate today.
Captain, this has been very interesting, but you know, looking at my watch, I think we need to be shoving off. So, do you have a clue for us?
Well, I think I might. On your next stop, you're going to be studying how early aviators and today's pilots navigate their ways through the skies. Now away with you!
I don't know, I don't get it. I mean, I don't see an airport and we're nowhere near any water.
Okay, Van, this one is your turn. How about you go in and check to see if this is the right location?
Okay. Well, there's a positive sign.
Van Hughes?
Yes. How do you know my name?
Well, I watch NASA Connect all the time. I'm Jane Garvey, head of the Federal Aviation Administration.
Oh, wow. Nice to meet you.
Nice to meet you.
Are you part of the road rally?
Yes, I am. I'm your next to last stop on your navigational tour.
I'm here to learn about how early aviators and today's pilots navigate through the air. Can you help?
Yes, I can. Just as Garrett A. Morgan improved roadway navigation and sailors built on early successes in nautical navigation, early aviators and the federal government worked hard to make air travel safer and more efficient. In the beginning, after the Wright brothers' successful flights at Kitty Hawk, the first pilots had no navigational aids. They simply watched for landmarks and followed roads, rivers, and railroad tracks. This approach to navigation obviously had its shortcomings. It only worked in daylight and in clear weather. In 1921, pilots for the U.S. Post Office conducted a daring experiment for night flying. Bonfires lit by helpful citizens helped to aid pilots flying the mail across the country. This approach was followed by airways marked by a series of light beacons. As technology developed, the government introduced still better navigational aids using radio. By listening to radio signals, pilots could stay on course even when bad weather kept them from seeing lights on the ground. Today's pilots draw on the advantages of GPS to guide aircraft along highways in the sky. The FAA and its partners, such as NASA, are working to build tomorrow's air traffic control system, which will draw on the benefits of the global positioning system.
Well, it sounds like I can do anything. How about the weather?
Van, everybody talks about the weather, but not even GPS can do anything about it. Weather is also a major factor with aviation accidents. But along with NASA, the FAA is developing several tools to give pilots more and better information on hazardous weather conditions.
Well, it looks like I've collected what I need. Do you have a clue for my next stop?
Well, your last stop will lead you to one of our partners who's working with us on GPS navigation. Good luck.
Well, thanks. Bye. You know, the more I learn about GPS and its everyday applications, the more I am convinced that I should get one of these for when I go on the road with my band, the Noodles.
Van, when Jane Garvey was talking about some special friends, she was talking about us, NASA.
Well, let's see who's here.
Hey, hi, are you with the NASA Road Rally?
Yeah, come on up.
All right.
Hi, I'm Dick Hushit, and this is Charles Howell.
Hi, nice to meet you.
Hello. Hello. You did a good job in navigating here.
It was as easy as a video game.
Right. Well, listen, here's our logbook. Now, according to the Road Rally rules, we're supposed to learn some information from you on GPS navigation. So our question is, NASA, how is NASA helping to improve navigation tools for aircraft?
Well, we have been investigating the use of GPS to help an aircraft navigate on the airport surface using GPS navigation, particularly in bad weather and foggy conditions. Here is an example of how this happens. As a NASA 757 approaches a runway, computer-generated graphics outline the correct runway and its precise location on a head-up display mounted between the pilot and the windscreen. Upon contact to the ground, a head-down moving map display shows the pilot his or her location on the runway and the taxiway system, as well as the location of all other aircraft. The aircraft location is provided by the GPS satellite navigation system. Digital data link communications are used between the pilot and air traffic controller, greatly eliminating the possibility of miscommunication. Using this system, taxi speeds can be increased by as much as 25%. Such a system will play a role in helping reach the goal of tripling our nation's aviation system capacity while maintaining safety in all weather conditions.
Dick and Charles, thank you so much for your time today. This has been so interesting. This whole road rally has been fun and informative. Thank you so much for sharing with us today.
You're welcome.
We'll see ya. Bye-bye.
You know, Shelley, it's really amazing how GPS keeps pilots on track in the sky. Sort of like managing flight traffic in a way not unlike the traffic signal Garrett A. Morgan invented for the ground.
Yeah, Morgan had a great respect for education, which he used to help others. Well, team, I think we did a pretty good job navigating in this road rally. But right now, we want to see just how good you can navigate on your own. We're going to send them on over to Northampton Middle School, which is located on the eastern shore of Virginia, where you're going to meet up with science teacher Barbara Haynes and her students who are involved in a navigational challenge. For me, I'm going to head on back to the NASA Connect studio. I'm going to walk back there, send you to the eastern shore, and Van, how about you park in the car?
Oh, well, sure. I think I might even check out a new location on my GPS.
Sounds good. All right. See ya.
Alrighty, bye.
Hi, we're students from Northampton Middle School, located in Matchapungo. NASA Connect asked us to investigate angles and directions by plotting a course on graph paper using a compass, rose, and ruler. Our goal is to establish 5 outdoor pathways mapping direction and distance with 5 separate teams using a compass, rose, and transit. We hope our 5 different paths will converge at a single point. Here are the materials for an experiment. 5 rolls of different color tape, 5 markers, tape, 5 compasses, 5 large compass rose transparencies, 15 pencils to be used as field point markers, 15 pieces of paper marked with the letters A through J, and 5 X's, meter sticks, 5 paper towel rolls, thread, 5 scissors, and before we go outside, we plot our course on graph paper.
We need to review some simple vocabulary terms to help us prepare for this activity. The bearing is position or direction of an object or point based on a compass reading. Navigation is the science of finding distance, direction, compass positions, and time of travel to establish a course or determine a certain position on a map. Triangulation is the mathematical and scientific determination of an unknown position using distance or bearings from known positions. A transit is a sighting device used in surveying to plot a course or establish levels or heights. Having reviewed these terms, we are now ready to divide into 5 teams. Team A, Team C, Team E, Team G, Team I. We divide tasks among team members before navigating our course. One person will call out the bearings and distance and takes care of field position marks. One person handles the compass and compass roads. The third person handles the transit sightings. A fourth person handles the tape rule and measurement distance. And a fifth person checks the transit sightings and distance measurements.
The first step in our activity is to create the transit. We take the paper tube and cut 4 slits into the end. Each slit should divide the diameter of the tube into quarters. Now put the string into the slits. This will create crosshairs, giving us greater accuracy as we look through the tube. Next, the tube is attached to a meter stick. We then mark 3 separate pieces of paper with 3 position letters for our group. Group A marks A, B, X. Group C marks CDX. Group E marks EFX. Group G marks GHX. And Group I marks IJX. These pieces of paper will mark the points on our course. Now we're ready to go.
Here are the procedures. Each group lines up exactly 4 meters apart with the letter designating our team on a line facing magnetic north. We mark our starting point and hold the compass over the starting point to confirm magnetic north. We also set the transit up at the starting point. Using the compass rose as our guide, we turn the transit to the first bearing on our chart. For your experiment, remember, north 0 degrees must always be pointing to magnetic north on the rose, the appropriate direction. We then use the transit as a sighting guide and direct the student with the tape rule to the appropriate direction. It's okay to use hand signals to direct the person left or right. Once we find our correct bearing, we measure out our distance and mark the point with a pencil and paper with the appropriate letter. We then pick up the transit and move to point number 2 that we just determined. We complete leg 2 according to the chart using the same procedure. When all the groups finish, we check for navigation errors. Did everyone arrive at the same point X? Now that we have finished our field experiment, we are ready to apply this knowledge to questions involving flight paths, distance, and time.
All right, joining me in the studio are some friendly faces involved with GPS. But before we talk to our researchers, let's give you a chance at some navigating that will involve calculating flight paths, distance, and time. Then after this segment, our two researchers, Dick Hushen from NASA and Hugh Bergeron from the FAA, will answer your email questions and take questions from some students attending a special anniversary event in Washington, D.C. as guests of the FAA. Okay, now, look carefully at the data, and using the information in the following diagram, work with your fellow students to answer the questions as read aloud by Mr. Rodney Slater, Secretary, U.S. Department of Transportation.
What is the total distance in miles of an airplane flight that starts at point C, goes through point D, and ends at point X? What is the total distance in kilometers? Now, here's a hint. Use the formula to convert miles into kilometers. How long would it take an airplane traveling at 300 miles per hour to fly from point C to point D? From point D to point X? How long would the entire flight take? How many miles are there in a direct flight from point C to point X? Here's a hint. Use the Pythagorean theorem to find your answer.
All right, so how do you think you did? Well, your mathematical computations and reasoning are going to be important skills to answering the questions. And speaking of questions, here with me now to answer some student questions are Dick and Hugh. So let's go to Washington, D.C. and meet up with a group of students from 14 schools that are spending a day with their adoptive business partner, the FAA, in a special event recognizing the 95th anniversary of the Wright brothers' first flight. On the stage, we have some important leaders to our country in transportation and research, and I'd like to take a moment to introduce our viewers to them. First, we have Mr. Rodney Slater, Secretary of the Department of Transportation. We also have Mrs. Jane Garvey, who is the head of the FAA. And we have Mr. Daniel Golden, the head of NASA, who also has a very special message for our viewers. Mr. Golden. Hi, Mr. Golden. I understand you have some words for us, for our viewers?
Yes, I hope all the students here in Washington and around the country, 700,000 of them, see the kind of tools we use at the FAA to make planes fly safer, at NASA to send the shuttle into space, and they understand that these are real tools and they're going to learn how to use them. And they also understand that if they understand how to use these tools, they'll have good jobs when they grow up and they'll be able to lead our country.
Mr. Golden, thank you. Those are very good words for our viewers. And now, beside Secretary Slater and Mrs. Garvey is a student whom they will introduce. They will have a question for our researchers back here in the studio. So, Mr. Slater, will you introduce your guest, please?
Yes. Thank you, Dr. Canwright. Let me just say that I'm here next to Anthony Marino, and we were listening and saying, these are some good questions, I'll tell you. Well, Anthony is a student at the Tuckahoe Elementary School, and he actually has a question that he'd like to ask. Anthony?
Thank you. My question is, how did we navigate before GPS?
Oh, all right. Good question. And let's see, who'd like to answer that?
You.
All right, you, all right.
The
That's a really good question, because before GPS, people did navigate. And so I think the best way to answer that is to take you back several hundred years ago and show you how some of the early people navigated. Well, one thing people would do is if they'd go to a certain location, as they traveled over the land, they would mark where they went and they'd make a map. And that would become a map and they could give to somebody else and they could navigate the same route. In fact, we still use that today. We have highways, that's a path, and we have road maps, and that's how we get from city to city. So you'll see some of these techniques, even though they're very old, they still use them today. Another technique was developed when we invented the compass. Now, the compass has a needle that points to the north, and if you know what direction you're going to go, you point in that direction and you see the angle, and that's called a bearing. And you follow that bearing, and then you can travel in that direction. Again, the compass is still used today. Any aircraft that you fly in will have a compass.
That's great. So what I'm hearing from you is some of the tools from the past are still being used today.
That is true.
That's great.
It's a combination of all of these tools, and they help back up each other and make sure that you have a more accurate path or direction.
Great. That's a good answer. And I know we've got someone else back there with Mrs. Garvey. So, Mrs. Garvey, could you please introduce for us your guest and then the question, please?
Well, yes, thank you very much. And I am joined by a wonderful young student named Brittany Jones. And Brittany is from Bradbury Heights Elementary School, and she has a question for us today.
Thank you. My question is, how does GPS work?
Great.
All right. How does GPS work? You got something there for us?
Yes, I expected this question, and I use this illustration to try to answer that question. The GPS satellite sends signals down to the Earth, and then the receiver on the Earth makes measurements on these, and the first thing it does is determine the distance or range to those satellites. And so let's let this wire here represent the range from this satellite, and this one the range from this satellite. Then with mathematical equations in the computer of the GPS receiver, it calculates where these ranges intersect, and that becomes your latitude and longitude of your position on Earth.
All right, and that's how Dan and I were able to get where we needed to go. All right, well, I see we're quickly running out of time. Thank you, Dick and Hugh. Oh, but I understand we have a special caller with a message. It's from Senator and astronaut John Glenn. Mr. Glenn, welcome.
Thank you. Glad to be able to participate this morning.
Thank you. I understand you have some words for our viewers.
I do indeed, and I'm glad to be able to give some encouragement to our young people today. You know, today is the 95th anniversary of when the first airplane ever lifted off the ground under powered flight. When the Wright brothers made that first flight from Kill Devil Hill down in North Carolina. And it wasn't a very long flight, but they were the first people to ever get airborne in a powered vehicle. And ever since then, we've been trying to go higher and faster and higher and faster, and we're into space now. And you might even look at the Wright brothers as the first astronauts, if you wanted to look at it that way. They didn't get where they were and make their discoveries by just having an interest in it. You know, they were people who studied things. They made little wind tunnels at the time. They did the mathematical measurements. They had to know their mathematics, and they had to have a scientific mind. And that's what we like to encourage in all our young people today. You just have to have the background that you get from school with regard to math and reading skills and all those other things. And that's the good part about being in school. You all have the ability and the place that you're at now in school to do all those same things and make tremendous contributions in the future, just like the Wright brothers did 95 years ago.
Senator Glenn, thank you. Powerful words there, and appreciate it. Now, if you want to discover more ways researchers are using GPS, then check out our website. And for those of you interested in the world of transportation, check out the online resources of our program partners. We're going to have to say goodbye now. Let's wrap up. Thanks, program partners, and all our guests. Thank you.
Our website. Here you will engage in an online road rally that will take you to 5 continents with a checkpoint on each continent as seen from space. Finally, for a videotaped copy of this show along with the lesson plans, contact the NASA Central Operation of Resources for Educators. You know, I wonder whatever happened to Van. Hello, Van.
Hello? Shelley?
Van, where are you?
Oh, I was just checking out one more stop on the GPS.
And where might that be?
what's a road trip without a milkshake?
Van, wrong answer. What is it that you're supposed to say?
Oh, well, we hope you join us next time on NASA Connect, when we connect you to math, science, and NASA. See you later. Thanks.